Hi, everybody. Thank you so much for coming in person. We have a fantastic in-person turnout and quite a number of people on Zoom, so thank you so much. Today, we're delighted to have Byron Wallace with us. Byron is the Cy and Laurie Sternberg Interdisciplinary Associate Professor and Director of the BS in Data Science program at Northeastern University in the Khoury College of Computer Sciences. His research is primarily in natural language processing methods with an emphasis on their application in healthcare and the challenges inherent to this domain. Without further ado, let me hand it over and we can spend this hour.
Thank you. Oh, well, that's premature. You haven't, it could be very bad. You don't know. Okay, thanks. Thank you, folks, for turning out on a slightly blustery winter day. Yeah, so happy to be here. And the plan today is I just want to talk a little bit about some stuff we've been doing on using large language models, which is obligatory in 2023, of course, to help physicians kind of navigate and make sense of different types of unstructured medical evidence. So, oops, did this not work? Maybe. Oh, all right, fine. Like this. There we go. So I'm going to talk about like sort of two types of unstructured evidence. And the first of these concerns reports of randomized control trials, or RCTs. And so these are sort of like published articles, a domain that I've worked on for maybe too many years. But I'll talk about some recent work there on extracting results from them. And then I'll talk a little bit about a line of work on trying to use language models to extract and summarize useful bits of evidence from electronic health records. And you know, I'll sort of situate that in contexts where we think that might be useful. So that's the kind of game plan here. I probably have too many slides as a forewarning, but I'll see. And the other thing is, if you have questions, just stop me. I'd prefer this to be interactive. So you know, that's my yes, please. Already. Previous slide. This one. Yeah.
So I think you use evidence, the same term, but two different meanings.
Yes.
The first one, the evidence in clinical trials, that's really, you know, robust evidence and global truths.
Yep.
But then the second sentence where you say summarize evidence,
yeah,
you really mean summarize data from EHR.
No, I don't. So the reason is it's a different use of the term, but that work, what we're really focused on is finding evidence that would support hypothesized diagnoses. So it's a different kind of evidence. It's not evidence about comparative effectiveness, although, you know, that's a whole different discussion.
It doesn't go through the rigorous evidence testing hypothesis.
This is just evidence for, like, let's say that you suspect a patient has a particular condition. The idea with this line of work is that you're going to use language models to try to abstract evidence that would support that particular diagnosis, not a treatment. It's not a, you see what I'm saying? So it is evidence, it's just of a different sort.
Different semantics.
Yeah, but I mean, it's evidence for a condition, not evidence for the efficacy of a treatment. Does that make sense?
Yeah.
I see your point though, but we'll get there. We'll get there. Cool. Yeah. So for the first thing, you know, I think I probably don't need to belabor this point. This is a now very outdated graph that I promise every time I give a talk that I will update, but I never do. But anyway, this is just showing the growth in the published medical literature. In particular, it's showing the number of articles that are describing the conduct and results of randomized control trials, or RCTs, in humans. And so I guess the main thing to take away from this is it's already a vast sort of evidence base, and it's growing quite fast. So it's increasingly difficult for, you know, practitioners who want to practice evidence-based medicine to keep a pace. And so for a number of years now, my sort of partner in crime, Ian Marshall, who is a real actual doctor, shown here, and I have been working on like a bunch of different language technologies to try to help folks make better use of this unstructured evidence base. And like most recently, we've been working on this thing that we call Trial Streamer, which is shown here. So Trial Streamer is like a living repository of all RCTs that have been done in humans, and it contains semi-structured data that we automatically extract from these sort of as they are published. And so we make both the database available, and we have this like prototype web interface. And the way that this works is we sort of monitor PubMed and other sources, like some clinical trial registries, to see when new articles are indexed. Most of these will not be reports of RCTs in humans, but we have a classifier that we've validated in prior work to identify articles that do seem to be describing new RCTs. And when we identify such articles, we pull them into Trial Streamer, and we run them through a suite of language technologies that extract various aspects of interest. So for example, these range from simple things like the sample sizes to more complex things like trying to infer the risk of statistical bias in the underlying trial, and also trying to extract the main finding, which is something I'll talk a little bit about in a moment. And we dump all of this sort of semi-structured data into the TrialStreamer database, and we make this publicly available. So this is TrialStreamer. And here's a sort of a screenshot of like the prototype interface that we have. And one thing it allows for is it allows you to do like faceted search. So you can be like, you know what, I'm interested in articles that or trials that are investigating, for example, COVID-19 as the population, as the condition of interest. And I'm specifically interested in the intervention remdesivir for whatever reason, right? And we can do this kind of faceted search because we have models that extract snippets that describe the populations, interventions, and outcomes respectively, right? And so this is maybe a useful thing to be able to do. In the era of language models that we are now in, I think what we've been kind of looking at is moving beyond this kind of semi-structured data and getting towards, like, I guess, the dream, which maybe would be being able to output on demand a summary synthesizing the entirety of the evidence for a particular well-formed clinical query. So for example, you would like to be able to just say, you know what, give me a summary of all of the evidence from RCTs concerning the use of triptans for migraines, right? And in this, so we have this demo paper led by Sanjana, who is a PhD student shown here, also collaborative with Ian and Jared. And basically what we did was we hooked up like a fine-tuned, relatively small-scale language model to TrialStreamer. We fine-tuned it on Cochrane systematic reviews, and we just passed through the top K retrieved RCT articles, and we output then a summary that looks like a Cochrane summary. Cochrane, for those of you that don't know, is an international nonprofit that produces medical systematic reviews. Kind of, that's their bread and butter. So we have this data set that we can fine-tune on. So, this kind of works, sort of, right? Like, so in this case, right? Like you actually get this nice summary if you read it. I believe in this particular case, this is all accurate. This is like what you'd want it to say. It like agrees with the Cochrane review on the topic. But it's not always the case. So this paper is sort of talking about how like, the problem here, as it will probably come as no surprise to you all, the problem here is that, you don't know when to believe the output and when not to. And now maybe you think, well, that's because you're using like a smaller fine-tuned language model. But we had this ACL paper that was led by Chantal, who was a PhD student of mine at Northeastern. And this was looking at, even these massive models, these proprietary models. So this was GPT-3.5, 4 wasn't out yet when we did it. But we had a paper at ACL over the summer looking at the degree to which you can just get these systems to produce kind of narrative synopses of evidence. And what we did was we took some Cochrane reviews. So we have the reference summary, we have the inputs, we have the narrative kind of reference that they wrote. And we asked, GPT-3.5 to produce a synthesis of the evidence of the input articles. And we then hired doctors to compare this to the reference summaries that were written by the humans, by Cochrane folks. And what we found is that in over half the cases, the generated summary disagrees in a meaningful way with the corresponding reference summary. So, these models, they also struggle to synthesize. It's a little bit funny because like at the same time, they're also marked as like largely supported by the inputs articles. That should say articles, sorry. So what's going on there? I think what's going on is like GPT-3.5 and GPT-4 anecdotally, what they like to do is just be like, well, study 1 says this, study 2 says this, study 3 says this. And it's like not what you want. What you want is like a synthesis to be like, well, on balance, the evidence says whatever. Now, maybe this isn't super surprising because these are models that are trained to produce tokens. So why are we asking it to do meta-analysis, right? So I think that's a reasonable point. And to that end, maybe what you ought to do, right, is think more about the tasks that you're actually asking it to do, which is to actually put together the results that are reported in constituent trials. And so we've been thinking about this for a couple of years now, is like basically like trying to extract the actual findings from an underlying trial report. And so we call this evidence inference. We have this data set that we assembled for it a couple of years back at NACL. And lately what we've been trying to do is design models that can consume a full text article describing a randomized control trial and output all at once the interventions that were studied in the trial, the comparators that they were compared to, the outcomes that were measured, and what the findings were concerning these. And so way back in what seems like forever ago in 2021, Ben Nye, who was a student of mine at the time, led this paper where it was like a nice, good old-fashioned kind of NLP system. It was a little bit of a throwback, kind of had like some co-reference going on, stuff like that. It kind of did this task okay, but it was still pretty bad. And I'm not going to talk about that, of course, because then what happened was it turns out that you can just throw language models at this and they do really, really well. So, so if you squint a little bit, this problem of extracting like, oh, what were the interventions, comparators, outcomes, and the results reported concerning these? If you squint a bit, this just looks like relation extraction, good old-fashioned relation extraction, where the interventions, the comparators, and the outcomes are sort of your entities, and significant increase, significant decrease, or no significant difference if you're doing the ternary classification thing. That's your relationship. And so my student Salman led this paper at ACL over the summer, where we weren't doing it in medical stuff in particular. I'll get to that in a moment. But we just said, well, like, how good are these models at just doing like good old-fashioned relation extraction? And it turns out, probably to the surprise of nobody here, that you can get state-of-the-art performance if you just linearize, and I'll say more about that in a moment. You linearize your relation extraction targets, and you can do zero-shot relation extraction pretty well, or you can fine-tune smaller models and also get state-of-the-art results. Right? And so what does this look like concretely? Well, this is an example in like classic NER. So you take in some input text and you run it through your LLM, and basically you're going to ask for a linearized output, by which we mean some kind of structured string where we're representing the entities in play and their relationship. In this case, Bill is a person and works for NASA, right? And so this is like literally what your target looks like. And, I guess, so this plot, what is this showing? This is showing the dotted line is sort of what was the state of the art on Connell. Connell is a standard relation extraction data set used probably for too many years in NLP. But basically what this is showing is that if you fine tune this generative model, which was Rebel, that was a BART-based model, you get performance around 75 F1 score. Few shot GPT actually out. So again, not fine-tuned on a large training set, but just like few shot, does a little bit better than this. And then here's the thing that's a little bit weird to me. If you elicit chain of thought style reasoning for relation extraction, this gives you a couple more points. I still don't really know why, but it does. So it'll be like, oh, well, this is like a person. Sometimes it'll make sense, but like relation extraction is a little bit of a strange application for chain of thought. But for some reason, this is what happens. So that's okay. I don't really care about GPT. Like, I want to get away from it. So I think the Flan results are more interesting. So if you just fine tune Flan T5 on, I think this is large, and you just fine tune this guy on the train set, you get about the same performance as Rebel, which makes sense. It's about the same size, I think. And so that's pretty much what you would expect. What's interesting is the pink one, the bar 4. Here, what we're doing is we're fine tuning Flan T5 on the true labels of the train set, augmented with chain of thought style reasoning elicited from GPT. You fine-tune Flan on that mixture of things. And for some reason, this gives you extraordinarily good performance, like many points, well, a solid 5 points above the prior state of the art. Why? I don't really know. So one of the things that we're doing right now is sort of like stress testing. What is it about distillation that allows for like the chain of thought style stuff to be so impactful? So we're sort of looking into that and doing all sorts of weird experiments where you like scramble the chains of thought and like seeing if you still get improvements. But this is kind of a mystery to me still, but it is what it is. And so you can do quite well. So that's kind of cool. Right. And so coming back to that was just sort of general NLP stuff. Coming back to the task that we motivated this whole line of work, what we want to do is we want to take in, an RCT piece of text, and we want to run it through our model, and we want to get these linearized outputs which codify the structured kind of results, right? So it's like, oh, this aspirin was compared to placebo with respect to the duration of headache, and there was no significant difference. And here's like a supporting piece of evidence. And the supporting piece of evidence, we want to be we want this to be extractive. So this should be a snippet from the corresponding article that one can look at to verify the conclusion that's being reported, right? And so we actually have these because we collected these for the original evidence inference data set that I mentioned briefly. So we can fine tune a model to do this. So we're not using like chain of thought style reasoning here. We're using this like, we're asking the model to produce the evidence span alongside the structured sort of relation triplet or whatever, or quad. So one thing that I didn't mention, but it's also true in the general case, but I'll highlight here, is that when you're doing relation extraction with like language models, evaluation is very difficult, right? And it's difficult because the model will generate whatever it wants to. So this is a real example where there was like a trial that was looking at body weight as the outcome. And for some reason, so the result was, the reference result was that it significantly decreased body weight, whatever the intervention was compared to the comparator. The language model decided that body weight reduction was the outcome, right? Which means that the direction is reversed. So now it's like, oh, it significantly increased body weight reduction. Now that's an awkward choice, but it's still technically correct. And so if you try to do like exact string matching and use in like sort of measure F1 in this way, obviously this is not going to work. So what we do is we actually paid a bunch of doctors to look at the references and the ground truth and decide if it was accurate. Yes. Yes.
I think, it really depends on how you define outcome. So it could be body weight. One option is to treat body weight as an outcome measure, and the other one is to treat body weight reduction.
Exactly. That's precisely what I'm saying. Yeah, exactly. But the thing is that the language model is unconstrained. So like, I think it's valid to treat body weight reduction as an outcome. It's a little bit of an odd choice, but like, it's not wrong. And so like the direction flips, but it's still correct, right? But it's difficult to measure this automatically. But yes, I completely agree with you. Yeah. Cool. So yeah, so evaluation, so we did it manually. That's kind of the only way to do it. And here's like a bunch of results. And I guess like the takeaway, the top 3 models are all like these bespoke architectures, like these neural architectures that we used to, remember that was fun when we used to do that and we used to build them. And one of them is Ben's, the student I mentioned earlier. And these models were all kind of like crafted for this or very related tasks, similar tasks. And, then on the bottom, you have like sort of language models of various sizes and pre-training schemes. And the takeaway is like Flan T5 large, when we fine tune it on the evidence inference set with the evidence bands, gives you like pretty reasonable F1s. It's a very challenging task, right? Like this is end-to-end extraction of the Pico elements and inference about the results. And we're getting about 60 F1 on the end-to-end measurement. And what I really want to highlight is that this is with the evidence spans when you fine tune it. When you drop the evidence spans in the targets that you fine tune on, you lose like almost 20 points F1, which is weird. Like I kind of get it, I guess. It makes more sense to me than the general relation extraction one, but this is still kind of a puzzle to me. I still don't really know why this matters so much. So I think we think this is interesting, but I don't have more substantial things to say about it, other than the fact that like it seems like when you're distilling or when you're supervising modestly sized language models, like having some sort of like explanation in scare quotes in free text helps for some reason. So that's kind of the takeaway there. The last thing I'll say is what we did was we took this model, which will yield like structured outputs for the results reported in trials, and we just apply it to everything in TrialStreamer. So this gives us like a database of these like structured findings that are saying, oh, this intervention was found to have this effect compared to this comparator on this outcome. And we apply it to all of TrialStreamer and we dump it into a database. We haven't really done anything with this yet. We just think it's cool. So if you want, you can play around with, the URL is hidden. It's a terrible URL, but there is a URL. So if you're interested, you could play around with it. Hopefully it's still, but I haven't checked for a while, but if it's not, I can make it, I can fix it. But yeah, so I don't know. We think there's probably cool stuff to do with this, but we haven't done it yet. And I think like, just to tie this back to the summarization work, like my thinking is probably what you want to do is condition your summarization on, these semi-structured outputs, right? So instead of just being like, here's a bunch of trial results, unstructured, like do meta-analysis for me, probably what you want to do is kind of guide the summarization through by conditioning it on like, here are the semi-structured findings basically that I've extracted. now generate the output, right? That's my sense. We're sort of working on that, but we haven't, I don't have results or anything yet. But that's kind of my my thinking. Okay. Cool. That's actually all I want to say about the trial stuff. Any questions on that before I move on to EHR world? All right. Yes.
Dr. Wallace?
Yeah.
Question, which is in general, there's this idea that data quality is important.
Yes.
And here you have like really good data. Like, is that the case that the data is really good?
In what sense? Yeah. So the question is about the data quality, and if here the data is very good. The data is data from trials that have been published. Now, whether or not that counts as good, I think that's when you get to the risk of bias stuff, for example, I suppose, right? Like, do you actually believe this result? Like, what's, is there a risk of like poor allocation concealment and things like this? And so we do have models that try to infer that. And like in Trial Streamer, we offer a sort by, you can sort the evidence by like the sample size multiplied by the risk of bias score, or like 1 minus the risk of bias score, right? So it's like big and high quality trials first. But I don't know, beyond that, it's hard to say, right? Like I think it's probably as good, given that these are RCTs, probably as good as it gets. We're introducing noise, of course, because all of these methods are imperfect. So I guess it depends on what you're doing with it as a downstream thing. But yeah, in general, I'd say the data is pretty good.
I guess the next question is then it wouldn't make any sense to like include things that are not RCTs. Like there's still like
there's a lot of evidence out there that's not RCTs. It's true. Yeah, no, you're right. I think it would. I think you have to just rethink. The nice thing about RCTs is like there's this whole like semantics, right? There's like the PICO, and there's like there's going to be like some comparative effectiveness estimate, and so you have this like really well-defined kind of like semantic space. And I think as soon as you exit RCT world, it's just like a lot messier. But certainly there's a lot of stuff that is not RCTs that you would like to be able to use. So, I think it's something that's been on our list for a long time, but we still haven't perfected the RCT stuff. So, but yeah, you're right, of course. Yeah. And I think yeah.
So I know like we tried on tasks related to like instructional summarization using GPT-4, but it's fine-tuning. Like
So GPT-4, so the question is if we've tried fine-tuning GPT-4. So you can't fine-tune GPT-4, right? As far as I know, unless they've changed this recently. GPT-4 allows you to fine-tune? Is that true? Can anyone vouch for this? Is this true? It's true? You can fine-tune GPT-4? Ah, that's cool. Listen, here's my take on GPT-4. I'm sure it would do better, but I hate it. Like I don't want to do it. So it would probably do better, but I don't think it's the interesting thing. But yes, I'm sure you would get better numbers. I'm sure you would. Yeah.
Yeah, I have two questions. One is like, did you try any domain-specific LM, right? Because FLAN-T5 or these things, they get trained on other.
That's a good question.
Data sets, like they show that NetPalm is like super good if you send me questions. So any like domain-specific LM that's already pre-trained on a lot of like medical data, does that help in your task? Yeah,
so the question is, did we use any non-generic LLMs like these medical specific ones? So anecdotally, yes. I'll talk more. Well, I won't really talk more about it, but like we get this question a lot. It's a good question. It's the right question. It turns out that these models, okay, I can't say anything about MedPalm, which is, I don't have access to. I'm sure that's probably pretty good. There's a bunch of these that are kind of out there that there are papers for and stuff. And then when you start to play with them, like they're really, and we have some work in the works on this, but they're not very robust. So these specialized language models that have been trained or pre-trained on domain-specific stuff, a lot of times, like they're not, just anecdotally, like, and again, we do have more non-anecdotal work eventually in the pipeline. I don't trust them. They don't work as well, basically. So somewhat surprisingly, the generalized ones tend to work pretty well. And the other thing is like the ones that are out there, like I know, no shade on, so Eric Lehman, who actually led the evidence inference work and is doing his PhD or just about finished up. And he has this like clinical T5, and that model's pretty robust, but it's not instruction tuned. So for a lot of the stuff that we've been doing, we need instruction tuned models. And there, in my opinion, there aren't really good options for like mid-scale open source instruction tuned models. clinical, I mean, or biomedical. There are some that exist that I don't think are super performant. That's kind of my short answer. Yeah. Yeah.
This is sort of my interest in clinical trials, but I'm just it's like a question of like data quality as time passes on. Like, are clinical trials data from 10 years ago, but 20 years ago, are there like seasonality within that data?
Yeah.
That you like consider like variance solution or
Yeah.
quality, some data, like some sort of model surveillance, for example, for trial stream.
Yeah, probably. So the question is about trial kind of formats, I guess, or like the sort of drift, I suppose. So there's two things there. Like one is like, I think one of the things I'd like to see more, I'd love to see like more meta stuff on like meta science stuff with trial streaming. We did a little bit with like, we had this BMJ paper about not real BMJ Global. And it was like, it's talking about like, you know, looking at like using trial streamer to say what conditions get the most in terms of like research with respect to like number of trial participants. And like, as you might expect, conditions that disproportionately affect richer countries, you know, there's more research in the sense of like number of participants in the trials. And anyway, this is the kind of thing that like, I would love to see more. We hope that more people will do this kind of meta stuff with trial streamer as a resource, but we haven't looked at like, you know, you could use the risk of bias scores over time, for example. Now that's kind of complicated because we trained that model on like a particular set from a particular era. So like you'd have to think about modeling that or whatever, but we haven't done it, but it's a very good comment. Yeah. And I think I'd love to see more like meta stuff with people using trial streamer. But yeah, it's a good question. I think there's a couple of questions in the chat maybe. Results. Yeah. Cool. So yes, somebody, yes, there apparently is our APIs. That's cool. I still don't want to do it. Even EHR between two hospitals with different outcomes would test on a model. I believe that's true. I don't know is the short answer to the question though. Precision and recall. Yeah, so the difference between precision and recall is fairly big. Is a task precision or recall oriented? Yeah, that's a good question. I think it depends on like what you'd be using it for. Like if you, yeah, it's a little bit of a tricky question. I think in the case of using it as inputs to meta-analysis, you probably want to have a little bit of a bias towards precision, but you know, you could of course trade these things off against each other depending on what you're using the actual extracted results for. So I'm punting on that a little bit because I think the real answer is it kind of depends. But for the intended use case that I have in mind, I think probably probably precision is what you'd want to favor, is my guess. Oh, I have one more question. Yeah, Kong, go ahead.
Hey, nice talk. So I got a question which is pretty high level, I will say. So I'm just wondering, what if we are entering into the LLM area, right? Do we still want to actually extract those pickle elements or whatever, you know, to calculate precision there, right?
Right. So the question is, why do we want to do the extraction still in the LLM era? See, that I tried to motivate it at the beginning, but I seem to have failed. So it's a good question. It's the right question. But like, right. So like, okay, we haven't done 4 yet because it wasn't out. But like 3.5, for example, still doesn't do synthesis in the way that we want it to do. And so maybe that'll be solved by even bigger models. I don't know. But right now, I kind of think you need to. I sort of think you need to do the independent, you know, the intermediate extraction. And I think you probably need to then guide the model to provide a synthesis of this. That's kind of that's where I'm at. Does that make sense?
Yeah, but I mean, in the future, my feeling is definitely it's more like end to end, right? So you have to embed actually the elements or all the more information than whatever you want to extract it.
Maybe. I'm a little bit more skeptical about that. Like, okay. I think it will training for next token prediction give you meta-analysis? Maybe. Maybe. I just don't know. But right now it doesn't. That's kind of my take.
Okay.
Yeah, it's possible. It's a good question.
Yeah. Dr. Wallace?
So there's been a lot of concern about clinical trials and representativeness.
Yeah. Yeah.
And so, you know, you brought up Pico, and there's been, you know, what I'm catching with a lot of the IPMO.
Yeah.
But, you know, is sort of trial streamer robust in the sense that we could sort of identify trials that have like more representative populations, things like that. So yeah, so the question is about
representativeness in the trial populations. So population is a tricky term to begin with because, typically that really predominantly refers to like the condition that you're interested in, like COVID. Of course, it also encapsulates things like, the demographics, and famously, for example, like women weren't involved in, weren't enrolled in trials for many years and so forth. And that's obviously a huge problem. This again to me would be like another case where I'd love to see some meta science using the trial streamer data. We do extract the population characteristics as part of the snippets that we dump into the database. So I think it would be really cool to look at like, this kind of thing over time, but we haven't done. But it's a great point, and it's something that I would love to see somebody do, maybe us eventually, but yeah. All right, let me move on a bit. Thank you for all the questions, but let me move on a bit to some of the stuff that we've been doing with EHR in particular. And so I probably don't need to belabor this for this audience, but like, this is like a nice, now kind of outdated New Yorker article about doctors hating electronic health records, despite the great promise they once had. And, there's been a lot of hype, of course, about the GPTs and so forth, language models in general, in terms of like being able to do medical things. A lot of this work kind of has a flavor of like, oh, we can get it to pass this like licensing exam or something. And that's like, it's cool, but like, we've been really focused on kind of practical questions. Like, okay, like, it's great that it can like pass the licensing exam, but like, how is this going to actually benefit somebody at point of care? And so we've been trying to think about this. And one of the aspects that comes up a lot is, of course, various notions of sort of scare quote interpretability, scare quote, because this can mean various things. I'll try to be very precise about what I mean when I say interpretability in the different contexts. So the first piece of work I'll talk about along these lines concerns, let me move this guy a little bit, concerns trying to use LLMs basically as feature extractors for relatively small linear models. So this is the idea. This was an EMNLP paper led by Jared and in collaboration with Jeff, who's a radiologist at Brigham and Women's Hospital, and Jan Willem, who's now in Amsterdam. So, right. So the argument here is that LLMs are great. We like them. But there are a lot of cases where you want to have like a small linear model that's defined over these kind of very clear high-level features. And there's a lot of reasons for that. Like one reason is like, you just want to be able to say, well, I've got a coefficient for this high-level feature. So like, I sort of know how to interpret the contribution of that feature, and I can sort of do sanity checks on it, right? As opposed to like, I have this 2048 dimensional embedding, and like, I have no idea what's going on. So that's kind of the argument. And the motivation for this was actually at a cardiothoracic ICU where they have this like risk prediction model, and this risk prediction model has been validated over in past work. And like I said, like, so you just have some small number of parameters theta, and you're just dotting that with some x, where x is like a feature vector containing, I don't know, order tens of features. And they really like this, and this is already a validated model, so they don't want to like drop in some huge language model to make this prediction. Right. And again, like the key thing here is like X, tens of features or whatever. You have these like really nice, clear features. Like maybe one is indicator for like, oh, this patient has a history of a chronic illness or something like that. Right. And so in their case, they actually have people that, this information like chronic illness history, like that probably isn't, in their case, it certainly isn't actually explicitly represented or encoded in the EHR. So what they actually do is they have people who extract these high-level features, and then this gets fed into the model. This is, of course, suboptimal, right? Like you don't want to do this. There's a delay. It's expensive. It's just not what you want to do. So presumably, you see where I'm going. What we're proposing here is to say, well, we like our small linear models. We like our high-level features. We still want the actual predictive model to be built over the high-level features, but I don't want to extract them manually. So what we're going to do is we're going to drop a language model for the human. And the language model now is just being tasked with extracting the high-level features from the raw data. So that's the idea. Yeah, and we still train the model over the resultant feature vector. Right, I should mention there was prior work by Monica and David Sontag and some other folks at MIT on just the idea of using language models for extraction, for data extraction. The kind of contribution here, I suppose, or the novelty on offer is we're really emphasizing the subsequent use, like basically using them as feature extractors for linear models, right? So we're thinking about the sort of end-to-end system where you're building a linear model on top of these features, as opposed to just doing data extraction. Okay, so I think this is like kind of an interesting hybrid, and it has pros and cons. So the pros, one thing that's cool is it permits like specification of arbitrary high-level features. So your domain expert can kind of ask whatever they want, right? This is also kind of a con, but I'll talk about that in a second. And it allows you to kind of capitalize on these large language models while still affording some type of interpretability. Here, what I mean is that you still will have a linear model where you have coefficients associated with high-level features. That's what I mean. And now the downsides. So first of all, feature extraction is not always accurate, right? You're like asking a language model to do this. Who knows if it's going to give you the correct thing? We have some results that say it kind of does, but The other thing is like interpretability is kind of weird because it kind of depends on how you set it up. For example, if you're trying to set up a linear model to predict the risk of mortality within 30 days, one of your features that you ask your language model could be like, is this patient going to die in 30 days? And that's weird because then you're basically just relying on, so you don't want to do that. My sense is like, I think that if you use language models as feature extractors for features that are verifiable from the local input and don't require like inference or like prediction, right? Then I think that's the better way to use this, if that makes sense. That's kind of like my view on it, but it's a little bit funny. Okay, so just to get a little bit more specific here, what are we doing? We've got, let's say, a feature N, and there's a binary or discrete version. And this is a lot of notation to say that we're going to have an indicator which says whether or not the response from the language model for some template for feature N, for example, the template might be, does this patient have a history of a chronic illness or something like that? That might be TN for N being the chronic illness feature. And X would be the patient record or some note from the patient record. This is just an indicator that says that the most likely response from the language model or the most likely next token is yes. Right? This is the simplest version. It turns out if you relax this a little bit and you use a continuous version, you'll get much better performance at the cost, arguably, of some of the interpretability, I guess. So this is a version that factors the confidence of the model into the feature, I guess. So you don't just have 0 or 1, you've got some scalar, which is the probability assigned to yes as the next token divided by the probability assigned to yes and the probability assigned to no, right? So this is like sort of allows you to scale it back a little bit. That's the continuous version. This is the plot that's a little bit hard to read, but let me walk you through it. So just focus on the right-hand side, the chest X-ray classification. This is like a toy task where we're trying to classify chest X-ray reports into various categories. And the star-spangled blue bar is the version of, is the sort of like linear model defined over the high-level features. We're talking tens of features here, right? Tens of features. And then we train it like usual. And that's to be compared, I guess, to the zero-shot black bar, which is just the zero-shot downstream prediction, just prompting the language model to actually do the task. So in this case, you do get gains by like training the explicit small model, which is nice. The two dashed horizontal lines are alternative approaches that use orders of magnitude more features. So this includes a clinical BERT model and a TF-IDF model with 30,000 features, 30,000 tokens. And so those do better, right? That shouldn't be surprising because it's like orders of magnitude more features, right? And so I guess like what this is saying is, you can get pretty good downstream task performance. You take some performance hit, but you're able to kind of be pretty competitive with much more opaque models. And maybe you don't buy that they're opaque because like TF-IDF, that's reasonable. It's like bag of words, right? But look, like here's an actual example this is from one of the mimic tasks. And on the left, these are the top features for the TF-IDF model. And you get like all sorts of stuff that's just really difficult to read. Like no is one of the top features. I don't even know what OSH is. Maybe I should. So this is like not great, I would argue, despite being bag of words. The ground truth, what does that mean? So in the mimic case, we use ICD codes as sort of like proxy high-level features, and then we pretend that we don't see them just to be able to evaluate. And so that's showing like when you have the ICD codes and you use those as predictors in lieu of high-level features extracted by a language model. And like those are just much more readable, right? Which is not surprising. And the far right is when you use the sort of inferred features. And again, like they're just much nicer to read, right? They're just like these high level kind of abstract features. So that's sort of the argument here. It also permits like, oh, what happened to my image quality here? PowerPoint has ruined it, but I'm sorry. So anyway, what this is showing is like a case where ostensibly this was a false positive because the linear model assigned edema to it. But on inspection of the individual high-level features, the radiologist was able to verify that those were accurate and that, in fact, this was not a false positive. Edema should be part of the label set. So, this kind of, I don't see how you could do that with like TF-IDF features. I think it's unlikely. So this is kind of we're sort of arguing for the advantage of this approach. You can kind of interrogate your predictions in a way that is pretty cool, I think. All right, so going beyond, like that's kind of like using language models as feature extractors for simple models. The next line, which is very related, is like using these things to aid diagnosis and basically using them as like fancy retrieval systems, right? And so this is work that's led by Hiba, again, collaborative with Jared and Jeff. And the basic idea here is to use LLMs with, use LLMs as kind of like evidence retrieval mechanisms. And the way that we do this, the motivating scenario here is that our radiologist collaborator, Jeff, he looks at a lot of imaging data, obviously. And his sense is like, there's a lot of information in the patient record that would probably benefit him in making his diagnosis, but he doesn't really have time to kind of go through the records, right, and find it. So the idea is to use language models to surface this evidence efficiently. And so the setup is like, we assume that Jeff has some diagnosis or hypothesized diagnosis, which I'll also call a query, in mind. So maybe it's like, oh, this patient has some sort of a hemorrhage. And what we do is we first just ask the model, like, hey, do you think that the patient is at risk for or has a hemorrhage? And the model will say yes or no. If it says yes, then we say why, basically. Or we say extract the signs of this. And that allows us to identify and actually produce abstractive snippets that say, well, the patient underwent surgery and is on some anticoagulation or whatever, right? And so this is the idea. And then we can show that to Jeff, and he can say, oh, that makes sense, or not, I guess, right? So this is the general setup. It's very simple. And just a little bit more concretely, we've done this with Mistral and Mistral Instruct, I guess, and Flan T5. And we say, read the following clinical note of a patient. Here's the note. Is the patient at risk of some diagnosis? That's initially hypothesized by Jeff, like a hemorrhage. And then we ask, okay, why? Why is the patient? We didn't do, it's funny. I think like, I'm not a big fan of like prompt engineering and stuff, but I think, I do think like it's interesting to think, you start thinking, the way that we've been thinking about this is you start thinking about these things as you are all of a sudden have these capabilities you really didn't have before. So like, how do these systems kind of fit together? And that's kind of we didn't do extensive prompt engineering here. You could probably get it to perform a little bit better, but I think it's really cool that we can do this kind of stuff now. Anyway, that's my aside. Okay, so we wanted to evaluate how well this very simple approach works. And so what we did was we took both data that we have from Brigham and Women's Hospital, which is private, and also for reproducibility, we again use Mimic. And we did some filtering to find cases that we thought would be kind of interesting to analyze. We ended up with like 8 instances from each, which I know is tiny, but it's extremely time consuming to do this annotation. So I think in all, it took the radiologists about 10 hours. And they're very time pressed anyway. I will say in the paper, we did some automatic analysis and we correlate it with the human judgments, and it kind of works. I don't trust it as much, even though it's bigger, but so I'll emphasize the manual of that. And the first thing we ask is, okay, is the evidence that is surfaced present in the note? In other words, is it not hallucinated? Because that's kind of important. And then we ask, like, do you think it would be useful? And I guess the natural question here is like, well, compared to what? What is our question? And to me, the question is, not the particular choice of LLM, because really these are like MLMs, like medium language models. It's really like, do LLMs or language models in general, do they permit like advantages compared to what prior to LLMs you would have used? And I think to me, that would be like some sort of neural information retrieval baseline, because really we're doing like fancy information retrieval. And so what we did was we took clinical BERT and we said, okay, we'll embed the diagnosis and we'll embed like a sentence, we'll do sentence by sentence and we'll embed each sentence in the electronic health record in the notes, and we will just dot them or whatever, or take some similarity measure. And that will be our baseline. We actually thought that was too weak though. So what we did was we augmented the diagnosis with risk factors. How do we get the risk factor? Of course, we have GPT-4 for the risk factors. This again is just for our baseline. So we say, what are the risk factors for like stroke and outcomes, a bunch of tokens, and we stick that into the piece of text that we run through clinical BERT. And this was all in service of trying to get a stronger baseline, basically. So we thought that was pretty good. But this is kind of like our IR baseline, just like embedding and dotting, basically. So that's it. And we want to know, like, is it worth using these reasonably large language models compared to these simpler approaches? And so this is like the annotation. We centered it like in a hypothetical situation. You can't read it, I'm sorry, it's very small. But basically we said, listen, the situation is that these are all radiologists doing it, but like imagine that you're in the emergency room, you're looking at a scan and you think maybe it's a hemorrhage in this case. And we have different diagnoses. And we basically just ask the questions that I mentioned. So we say, is the evidence present in the note? Yes or no? And note that the answer basically has to be yes for the IR baseline, because we're just like literally it's just extractive. So, but we still ask them that, just to make sure. And then is the evidence use relevant, basically. So that's kind of the setup. And here, large academic medical centers, the Brigham and Women data, that's for anonymization reasons. And Mimic is, of course, Mimic. And basically what this shows is two things. One is that the language models, they both are better at retrieving evidence that the practitioners found either very useful or useful. Weak correlation is this weird case where it's like, it's plausibly connected. There's like a lot of these cases where it's like, oh, I don't know, they have like a headache, or they had a headache at some point. It's like, like that's not related, but it's also probably not that relevant. So that's what weak correlation is. But generally speaking, the language models do better than CBERT, which is the clinical BERT baseline, the neural IR baseline, in terms of finding relevant stuff. But the black bars obviously are not present for clinical BERT because those are hallucinations. So that's not great, right? And in particular, here's an example, the bottom row. This is a real case where it was like a hemorrhage, and the language model is like, oh yeah, the patient has a brain tumor. But Jeff, the annotator, went through the entire note. This was not there. This is just completely confabulated. So that's, it's not great. And here's another example where the model comes up with like, oh yeah, so there's degeneration and numbness, and tingling of the arms or whatever. And apparently this is all very plausible. Like this would totally support the diagnosis, but like, no, just completely made up. So this is a problem. Fortunately, and this is cool, I didn't expect this. So in this case, I'm not saying this will apply to other cases, but for this task, if you take the hallucinated evidence on the bottom and the evidence that was not hallucinated, that was present on the top, and you look at the normalized token likelihood under the model generating it. So this is for Mistral Instruct, but results are analogous for Flan. And the two different colors are just the different data sets, the BWH and Mimic. And what this says is that like you can use that score, just the stupid likelihood assigned to the sequence under the model, normalized for length. You can like get an AUC that discriminating between the hallucinated and non-hallucinated content in this application of like 98, which is like fantastic, right? So basically you could just refuse to generate anything in the case where you likely were hallucinating. So we think this is cool. Like I was very surprised that this did this well because it's so simple, and probably reflects like the task specifically. Again, I'm not saying this is true for like all language model stuff, but for this particular task, this is like one way that you could just avoid hallucinating. Yes.
So in this case, like the type of hallucination is, you're saying like it was purely hallucination for the patient specifically, could be medically relevant, but
That's right. In fact, it usually is medically relevant. So because the model has some, incredibly to me, even these general models, they tend to have like this surprisingly subtle knowledge. And so they will hallucinate plausible things, but they're hallucinated for that patient.
like what's the input exactly?
Yeah.
I'm thinking of time
We-
in particular, like, I mean, that's not a good example. A brain tumor is a brain tumor. is a
Yeah,
brain
yeah, yeah.
tumor, But like something that happened.
We go back to so the input are like the individual notes from the patient's history, and we do them like one at a time basically, and then we do like an aggregation and present the most salient stuff. Yeah, yeah,
And so how do, you know, we
Yeah.
know there's no temporal reason here, but.
yeah. There's no temporal reasoning.
But like, how do you think it works out? Like, I don't know exactly the type of questions that are asked.
The question is literally like, first we just ask like, based on this note, is the patient at risk of this? For each note, we show it independently. And then if it says yes, we say why. And then basically it will provide an explanation. And now you might ask like, why bother with abstractive at all? Which is a very good question. But the answer is that, well, you probably all know, you look at the notes, they're terrible. Like they don't want to look at the snippets, they're very confusing. The actual like text that's generated is lovely. It's like, well, the patient has a history of this. The problem is sometimes it's made up. But yeah, when it is right, it's very nice.
But it feels like even that, you know, there could be something that's correct, but happened 5 years ago.
Sure, that's not relevant anymore. Yeah. That's a really good point. Yeah. So the question is about like temporality, like if something is really outdated. Yeah, it's a good point. We don't deal with that here. Right now, I think operationally, we just said like, if it seems relevant, like ignore the time basically, but you're totally right. That's kind of like I guess like to me, I feel like you could probably deal with that by sort of like limiting how far back in the record you go, depending on the condition, but maybe it varies on the condition. I don't know. It's a good point. That is a degree of subtlety that we did not consider in this evaluation though. Yeah, but it's totally fair. Yeah.
Yeah, I guess like the hallucination problem is really important. So one question is like, because you were already doing question answering to extract the features.
Yeah.
Have you guys thought of doing some sort of like self-verification, which a lot of papers are doing now to reduce hallucination?
Yeah.
When it says the patient has a brain tumor, as a next step, you ask like, does the patient have a brain tumor given the EHR? And
Yeah.
it says no, then it's sort of like presents conflicting evidence.
So
like
yeah, so it's a really good point. We had all sorts of discussions about like, how are we going to mitigate this? And like, let's use like these cool techniques. But then what happened is we saw this plot, right? Like, I don't need anything else. This is great. This is great.
Yeah.
I'm done. So we didn't, because in this particular case, for whatever reason, this works really well. I don't know. But yeah, you're right. You could do fancier stuff, but I feel like it's not going to get any better than this. Okay, I'm not going to actually talk about this. I knew I had too much stuff because I wanted to sneak this in. I knew it was audacious. Let me just give you the high level vibes. The last thing that we're doing is like kind of combining these last two pieces where what we're going to do, this is a confusing plot, so I'm not going to try. Okay, what we're going to do is we're going to design a neural additive model, which is basically modeling the likelihood of, let me get to the equation, actually, it's easier. Yeah, the probability of a condition. What we want to do is have like an interpretable, scare quote, model. And by interpretable here, what I mean is that we have a bunch of evidence chunks indexed by J, that's E sub J. And what we're going to do is we're going to have a weight vector associated with each condition that we might want to predict. And we want the prediction to be an additive combination of the individual contributions of those pieces of evidence, right? And the reason that this is cool, so BI is like an intercept for that condition, right? And so that's like the prevalence. And then everything else is sort of like how much this piece of evidence upweighted or downweighted the likelihood of condition Y sub I. And the way that we can do this is we use the previous stuff to extract the snippets EJ, right? Because we can just ask for the evidence for different conditions. And then we can, for example, quantify the contribution of a particular snippet of evidence that was generated by the model or provided by the model. And the reason that this is, one of the reasons this is cool is because then you can like rank your evidence in terms of like informativeness by just like summing over all the conditions of interest and looking at basically the magnitude, positive or negative, in terms of how much it shifts your prediction. This is like the log odds, basically. So this is kind of cool. It's something that's ongoing. I know I won't actually get into it because of the time. It kind of works. It's cool. I can talk more about it. We have a preprint if you're interested, but that's it. So the takeaways, I think LLMs are cool. I think there's like all sorts of tantalizing possibilities. I'm really into trying to think about like how to use them practically. So that's been the flavor here, is like just really thinking about like how to use these as system components, I guess, in a lot of ways. And of course, as you probably know, the big issue here is like sort of plausibility, or sorry, hallucinations. And I think we need steps for verification. And in some cases, quantifying uncertainty seems to work quite well, actually. That's it. Thanks to everyone who actually did the work that I'm taking credit for. And I will take any questions because we have like 5 minutes. Thanks.
So is it common now, like the clinical notes from EHR can be fed into large language models? Because I thought there was still some patient privacy issues remain to be resolved.
It's an excellent question. The question is about patient safety and large language models. And what I will say is one of the reasons that we prefer these like medium language models, we run all this stuff locally at Brigham. And like we can do that with like a Mistral. We can't really do that with like a, I don't know, 70 bill model. But that said, to be fair, you can get HIPAA compliant GPT-4 instances now through Azure. So that is an option. But who wants to do that? Yeah.
Thank you.
Yeah.
I missed your explanation, but I'm just wondering how do you determine the weight vector
For which?
for the RNN?
This thing?
Yeah.
So the weights, these are learned. These are the parameters of the model. Yeah. So, right. So that's kind of the whole thing. These are going to be weight vectors that have the same dimensionality as your embeddings. Yeah, I glossed over it obviously, but here what we do is we take the evidence that's extracted from the language model using the approach described. That's like a snippet of text that's generated under the model, and then we run it through an encoder. In this case, we're using Clinical BERT, and then we basically dot that with a weight vector that's learned per condition, and that weight vector is going to have the same dimensions as. So you're going to have number of conditions by embedding dimension parameters.
Thank you.
Yeah. Cool. Other questions? Yeah.
Yeah, just like from your talk in general, it seems that in several cases LLMs are helpful. So as a future direction or a next step, like because recent work shows that for alignment you don't really need a lot of data. Like I guess there was a paper from Facebook called Lima that said less is more for alignment. So have you thought about like collecting some high quality data, getting it annotated by medical experts, and then sort of like doing like RLHF using the DPL stuff, which is a lot easier now, so that it's more reliable and trustworthy than like GPT 3.5 or 4, where we exactly don't really know where they're getting their.
Well, that's why we're not using those. But yeah, so RLHF, maybe like, I guess my feeling is, here's one concern I have. I kind of think that if you fine tune the models on a small amount of data, I'm a little bit worried about brittleness, and kind of I think that's what's going on with these domain specific ones where people take like Llama and then like do like weird clinical training. And I think what happens is it like breaks a bunch of stuff in ways we don't know. And then you end up with like even more unreliable things, but I don't know. But yeah, you're right. I guess it kind of depends on what you're after. But you certainly like fine tuning for evidence extraction, for example. Obviously, that's helpful. That's a case though where we're not trying to use it for general tasks. We're just like really using it for, this is all I want you to do. This is like your sole task. So I guess if you start fine tuning it for general use, I'm a little bit more nervous about doing that, I guess, if that makes sense. Yeah. Cool. All
Dr.
right.
Wallace?
Yes.
Would you please say more about evaluating language models' capability of synthesizing information from clinical trials? Especially, I looked at one of your paper, GPT cannot synthesize RCT, something like that.
Yeah.
So one of my concern is that while we human are synthesizing information from RCT, we kind of judge the quality or whether the RCT is eligible for synthesize or not, right?
Yeah.
I wonder where you are evaluating language models, do you still do the same thing in the pre-processing, or you just dump all the available RCTs? And how did you do this? And
Okay.
Yes.
Yeah. So I'll repeat it for the room. So the question is, in this case, like one of the steps in synthesis is to make sure that the evidence that you're synthesizing is eligible for the inclusion criteria of the systematic review. And that's a completely valid point, and I kind of glossed over it. What we're doing here is like simple with respect to that, because we're taking the inputs associated with a particular Cochrane review. So they've already done the screening work, so the inputs are fixed. We're not asking the language model to do that task, although you could. That's like a different consideration. But here we know the included trials in the original review, and we are asking GPT to synthesize those specific trials. Does that make sense?
Yes, but still, even in conquering systematic reviews, when the authors include a set of clinical trials, some of the clinical included studies, well, the authors consider them in the first phase, but they may consider them as ineligible because of the smaller size of sample or failing to report the outcome to be observed. Right.
Yeah, so these are the trials that went into the meta-analysis, which we know because we have the Cochrane database.
Okay.
Does that make sense?
Okay. Thank you.
Cool. Yeah, good question.
The Cochrane database is not publicly available.
Yes, the Cochrane database is not publicly available, but I have it. I used to have better connections than I currently have, but yeah, we have it. Yeah. Cool. All right. Thank you everyone for coming. Thanks everyone online. Shoot me an email if you want.